creating using LC operations. So that's that was on the archive on our last one.
Okay, maybe let's slowly get started while people are finding their seats. Yeah, so welcome to the last session of today. So we're very happy to have Brad Lackey speaking about quantum Lego. Yeah, so please take it away.
Right. Thank you very much. It's the opportunity to talk here. I wasn't expecting to talk about quantum Lego, but it's one of my favorite topics, so I'm happy to talk about it. We got actually 4 papers on this subject over the past 4 years with my colleagues. And so with a half-hour talk, I'm going to cover some cursory elements out of each of them. I don't think I'm going to go deep on any of the subjects. And so I encourage you, I'll have some of these again at the end, take a snap and have a look at the papers. Okay, great. So what I'm going to talk about today is actually building quantum codes out of tensor networks. It's actually relatively straightforward. It's linear algebra as one would expect. But then really the meat of the topic is going to be about, well, how do I tell when the codes I'm constructing are any good? Okay, and so we're going to go through the concept of weight enumerators and their generalizations. And then I'm going to show some enumerators for scaled up codes, perhaps at full size, depending on the protocols you use. All right, so we've already talked a little bit about tensors and tensor enumerators. Naomi covered that this morning. So from our perspective, the tensor is just going to be a quantum state. So in this case, our T is our tensor, and the I's are just going to be some basis that we select from our space. A little bit later on, we're going to be a little bit more clever about what space we're talking about, what basis we choose, and so I'm going to indicate now to keep this sort of idea in mind. And so the whole principle behind this is we want to create complex things out of simpler things. Okay, so in this case, we might say, take a bunch of low-dimensional objects, little tensors, if you will, and trace them together. So this matrix product state is, of course, the product of all of these matrices. But if we think of these alphas as being indices for various legs, like down on this picture here, this first matrix can be thought of as a tensor with 2 of the horizontal legs here that are eventually going to get traced, and then one of them which corresponds to our basis that we're going to construct. Right, so the matrix product here is then going to be the trace over the alpha 2s in the sense of a tensor trace of multiple indices. It's a little unfortunate in this subject that trace gets used for about 4 or 5 different operations. It's just the way it is, and so hopefully it'll be clear enough by the context as we go. All right, so in the end, we are going to trace all the way through here and end up with just a state. Okay, and so this concept is going to carry over to quantum codes in a very similar way. And so we're going to use the notation NKQ for a quantum code that we've already seen a lot today. Q is going to be our local dimension. And so our Hilbert space here might be Q-dimensional, it is Q-dimensional. But I'm going to view the code as, in fact, an isometry, if you will, between k qubits or k qubits or q kits, I'm not even sure how to say that, into an n-dimensional object. So the dimension of the code is k and the length is n. And so we think of this thing, it's a linear operation, but the linear operators are themselves a vector space, so I can still think of it as just a state. Right? So in this case, my indices, I just transform in a slightly different way and list the input indices here and the output indices here, and this code is then characterized by this. And so those of you familiar with the topic, this would be like the choice state of the encoding map of the underlying code. That's just the state that it is. All right, so our goal is exactly what I said. We're going to build large codes out of small ones. Our codes are going to be traced together like we just did with the matrix product state. We take smaller codes, we choose some legs, and we trace them in exactly that tensor network idea, that tracing idea. The check matrix is easily constructed from these. This is just linear algebra. So you take 2 matrices and you just manipulate them in the right way, and you get the new check matrix for a new stabilizer code. The logical operators are relatively easy to analyze through a concept of operator pushing. I'm going to cover that in the next couple slides. But the real issue is I end up with a check matrix of a new code. I don't really have a lot of information about how good the code is in terms of its distance or other properties. Okay, and so what our goal is here today is to show that the weight enumerators of these big codes we construct out of these tensor networks can be computed by tensor network methods from the enumerators of the small constituent codes that we begin with. Right, so that's really what we're after today. All right, great. So it seems like the 2x2 Bacon-Shor code is the code of the day. It's, I think, appeared in almost all of the talks. And so no surprise, we'll deal with it in detail again. So here's the stabilizer for this. If we view this thing, it's not really a ZX diagram way, but it has the same features in that the logical operations we attach as legs, and so in this case, the vertical legs going up and going down can be thought of as the logical qubit and the gauge qubit of the Bacon-Shor code, while the 4 physical qubits are in a plane. Okay, and so that's represented around here. And so like you would glue together the fundamental spiders or something like that in a ZX diagram, you do the same thing of gluing together the small codes by tracing their legs together to create a larger code. We have a completely static view here, unlike the ZX diagrams, which would be thought of as dynamic, actually writing out a circuit. Here we're just explaining this tensor which describes the underlying code. Okay, so let's focusing on the left-hand side here. This diagram indicates a stabilizer for that tensor which describes the code. Okay, so in particular here we have the logical Z operator on this Bacon-Shor code is represented by 2 physical Z operators, in this case on qubits 1 and 4. And so labeling the appropriate way they're here. And so having this logical Z and these 2 physical Zs then stabilizes the choice state or the tensor that represents the underlying code. Now we can really think of this as a dynamic thing, and then we're going to do that, and that's the Genesis operator pushing, is that if this is a stabilizer for the code and I write down a logical Z and I want to understand how does that logical Z operate on the underlying code, since this stabilizes it, I can imagine taking this Z and then pushing it through this figure and out the 2 legs, and that gives me a physical representation of the logical operator. Okay, and so similarly with X, but it goes out a different pair of legs in this case. Okay, great. All right, so doing this a little bit more formally, these operator pushing, here's a couple examples, and this should be relatively clear now how all of it works. I can create new stabilizers for a post-traced code. So here I'm tracing 2 legs of the Bacon-Shor code together. And the idea is I start with a stabilizer on one of these codes. And so the all Z's has no logical operation. So it's the identity on the logical and the gauge legs. This Z then pushes across the trace to a Z here, which then I can push out to the 3 legs. And I discover that the all Z operators is going to be a stabilizer for this new code that we've obtained by tracing together 422 codes. Okay, great. In a similar way, we could find what one of the logical X's look like. Again, we just take our X, we push it down using the stabilizer rules for the underlying tensor. This one goes out to the boundary, if you will, right away. This goes through the traced operation, and then I use a stabilizer to move it to the boundary. And so again, I get a physical representation of the underlying logical operator for this construction. Okay, so in this case, this is an example of one of these N-2 codes that was in Mike's talk this morning. And so these can be constructed by just gluing together as many of these 2x2 Bacon-Shor codes as you want into a chain to obtain that. So as a consequence, the thing constructed by concatenating surface codes with these is going to be a good example of a candidate of a code constructed by this Lego formalism. And so its enumerators should be very accessible. Okay, in fact, they are very accessible. All right, so similar types of constructions. Here we see a surface code. Now, here again, we're just taking our little 2x2 Bacon-Shor codes, 422 codes, and we're going to glue them together. But if we give a little twist between alternating ones, then this operator pushing these logical Z operators are going to come out and push through the legs, and they're actually going to end up in a loop and cancel each other in the center. And so what we have is 4 of these gauge operators, these 4 Z operators, that have no effect on the boundary whatsoever. Okay, so that indicates that these are going to in fact be stabilizers. They're going to be a relation on those 4 gauge qubits. And so this relation then can be identified with, in this case, a plaquette operator on the surface code. Similarly, we have the X operators, which push into this closed cycle that have no effect on the boundary, so they become a relation on those, and it can be identified with a vertex operator, again on the surface code. All right, so this really shows some interesting features when we do this, because now the gauge operators we're actually identifying as the physical qubits on the code after we do the traces. All right, so similarly, we would have logical operations on the logical qubits pointing upwards, and they would collapse. I'm not showing those, but in fact, there's only one logical qubit after you perform the appropriate traces on the boundary. So in this case, for instance, we could construct the toric code by taking one of these legs and then tracing it around to the corresponding leg on the opposite boundary, so that all of the physical qubits in what were the original Legos are now gone. Right, so the gauge qubits become the physical qubits for the post-trace code, and the one logical qubit becomes the logical qubit after you apply all of the relations. And so, the toric code and the various surface codes can be realized through this Lego construction, and therefore they're amenable to this contraction type principle for their enumerators. And so I'll give some concrete examples of some large enumerators for surface codes a little bit later. Okay, variants on the surface code. Anytime you do local operations on any one of the pieces that go into this construction, it's not surprising that they have virtually identical formalisms. And so the XZZ code here, it's exactly the same network. It's just now local changes in the Legos themselves produce different logical operations, different, in this case, gauge operations that get glued together in a slightly different way, but give exactly the same type of tensor network to build those codes. Triangle code or twisted code, take a little gadget here, and so this 4-1 gadget allows us to glue together these 2x2 Bacon short codes in a different way. An interesting feature here is that we need to add an additional piece. Instead of just tracing these legs together usually, we have to put a little Hadamard in there and trace that as part of the process, and that's going to switch, pushing across that leg, the X's to Z's and vice versa. And that's going to be necessary to recover the proper stabilizers and logical operators for this type of code. Okay, nothing special about those type of codes. We can construct other codes. For instance, it may not be clear that you should be able to construct a color code from the 2x2 Bacon Shore codes, but in fact you can. Recall that the concept of the tensor, the logical legs and the physical legs were intermixed. We didn't really specify one over the other. We did in the diagrams, but really the tensor itself doesn't really separate those two. And so there's nothing wrong with taking our 422 codes and tracing together the logical and the gauge legs. And a consequence of which is we end up with an 8-qubit code. Now this, 8-qubit state, I should say. This state is incredibly symmetric. And so just pick one of them. And so in this case, pick leg 8, and we'll just declare that to be the logical qubit of a new code. Right? So that's exactly the Steen code. And again, illustrates the point that things that exist on the Lego, in this case, stabilizers on the individual Legos, don't necessarily correspond to what you'd think they would in the post-trace code. So for instance, we know that say all Z's on the first Lego here, 1, 2, 3, 4, that's a stabilizer here. And indeed, that corresponds to a stabilizer on the post-trace code along this green plaquette. But if I look at the same stabilizer here, but on the other code, the stabilizer on 5, 6, 7, 8, on the new code, well, that's actually a logical operator. So it's supported on 5, 6, 7, 8, connecting the boundary and the logical leg. Right, so it will mix up these sort of logical representations of qubits as well as stabilizers. But at the level of tensors and the networks themselves, those are all equivalent. Those are all the same thing. All right, great. One can show that there is a notion of an atomic Lego. And so here's a couple, so say a family of 3 different ones. Say pick any 1 qubit state you'd like. A family of unitaries and say the GHZ state. GHZ state can be just viewed as the tensor corresponding to the repetition code, trivial repetition code. And so these are enough to actually build all codes. So all codes can be formulated as these Lego constructions from basically just these 3 very, very simple ones. Now, I don't have any bounds to say how many of these things I have to construct to be able to achieve any code. It's certainly not the case that I can just grow it from below. It may be that the codes I construct have to get very, very large before I start tracing legs together to be able to recover the proper stabilizers and logical operations. That may very well be the case. So here's an example of how that actually happens. Let's say we take our basic 422 codes, but rather than just tracing one leg, let me trace two of them. Right, so what looks like here an interesting logical operation, namely I look at the logical operator where I apply X to both of the codes independently. I can push this one down and it comes out to the boundary, and I can push this one down and it comes out to the boundary. That's great, but I have another choice, right? I could have pushed them to the inside. And if I push these X's to the inside, they would have canceled the middle. And so that shows us that the two logical X's on each of these is in fact a relation. Okay, so it's trivial. Right, so as a consequence, when I trace these two legs together, in fact, this degenerates, and I get another copy of the 422 code again. So it may be that as you build these very, very large tensor networks, after you apply these relations, they could collapse down and become very, very small things. So as a consequence, if I just write down a code and say, well, how do I build this as a tensor network? It's not clear that there's any bound on how big of a network you have to build before you can trace to something that recovers the code. All right, so that's actually pretty good because it doesn't violate huge numbers of complexity theorems that say constructing codes is hard. All right, now to get to the sort of meat of things. Quantum weight distributions, these were introduced by Peter and Ray some time ago. So here, error basis is sort of a technical thing, and so if you're not familiar with what an error basis is, just think polybasis. Okay, so in fact, this is over higher dimension, and so if you're happy with Q local dimension, this is like the Clifford-Weil basis on Q elements. Here, I say arbitrary Hermitian operators. This is at the level of generality that they worked at, but in practice, we always take these Hermitian operators to be a projection onto the code space. Okay, so if I define this quadratic map by tracing Pauli operators of weight D against the projection onto the code, you wouldn't think that this necessarily tells us anything interesting, but in fact, this A does actually compute something very interesting. This essentially computes the weight distribution of the stabilizers, of stabilizer code, up to a normalization term. Okay, if I multiply them together and then take the trace, something very, very similar, that computes a slightly different distribution, and this in fact is going to be the weight distribution of the normalizers or the logical operators on the code. If you want to compare this to the classical theory, so it's in fact a little bit of the reverse of what you'd think. It's the B operator, which is like the traditional weight distribution of a classical code, and then A is like the distribution of its parity checks. I guess not surprising in hindsight because stabilizers are sort of like parity checks of a code, and so their weight distribution is captured in the A. Okay, great. So these are quantum weight distributions. We usually package these things up in terms of enumerators. That is just generating polynomials for whatever these numbers are. And so I think I'm not going to write a huge number of examples out right away. There'll be some examples at the end. And so the count of the stabilizers at weight D is the coefficient in front of Z to the D in its enumerator polynomial. All right, so a quick example that isn't the 422 code is the perfect code, 513. It's sort of the second simplest one to analyze. Oh, didn't realize I was up on a podium here. And so here's the generating set for its stabilizers. If I just look at all of these, we see that they're all weight 4 in the sense that one of their operators is the identity, the other 4 are not. This is just a generating set. If I multiply these together in all possible ways, I'll get a whole bunch of other stabilizers. Turns out all of them have weight 4. And so the A enumerator, counting the various weights, there are 15 stabilizers of weight 4, and of course there's the identity, which has weight 0. There is a normalization term out here, which I've just chosen not to include in the definition, which does get in the way a lot of times. The logical operators one can compute directly. I mean, it's not hard. This is a small code. But in fact, we don't ever have to compute this. It turns out that the B is entirely derivable from the A through a very straightforward transformation. Okay, so in this case, we can see that there are 30 weight 3 normalizers. These weight 3 normalizers are not in the list of stabilizers because there's no weight 3 things there. And so that's a great indicator that the distance of the code is in fact 3. But better than that, we can actually get a count of all of the non-trivial operations at weight 3 that lead to non-detectable errors. All right, and so so a couple of quick results. I want to skim over these owing to time, but these enumerators are actually LU invariants, and so they don't actually capture all the details of the code. They just capture a certain number of them. Here's the statement, and this is sort of a meta theorem. If you ever do anything about weight enumerators, you're obliged to prove something called the McWilliams identities, and that's exactly what these are. These are the analogs of the McWilliams identities for quantum codes. It says that the B, after homogenizing and introducing a homogenizing variable W, can be obtained through this transform of the A. So it's just a polynomial transform. All right, great. So moving right along, yeah, here's basically what I said, is that the weights of the stabilizers in weight D is captured by this weight, this quantum weight AD, and then similarly for B. So if I take the difference of those two things after fixing the normalization, I am very literally counting all of the normalizers which are not stabilizers. And so in particular, the minimum degree of that is going to be the distance of the code precisely. But in fact, since we also have all of the higher order things, it can be this can be refined to a very concrete statement about the exact probability of an undetectable error. It is just the evaluation of these polynomials under sort of the whatever error model is appropriate. And so in this case, a uniform poly-error model or error model under depolarization channel. Okay, great. Right, so now just extend this in the most natural way. So we want to build tensor networks that lead to new codes. Well, those tensor networks can also build tensor enumerators. Okay, so here we take a subset of the legs J. Those are our tensor indices. Now we have to be a little bit clever on the basis that we choose for these. Before it was just sort of just a standard qubit basis. Now I'm just going to have to give them names. And so let me just call these basis elements E, and notice that they're indexed by a pair of poly operators. Okay, so for local dimension 2, each of these guys is going to be 16-dimensional. So we have a little bit of a dimension creep going on here. Okay, so to define the tensor enumerator, we trace all of the legs that are not in the enumerator in the following sense. Just for a little bit of notation, I'm going to write tensor product J to say that the factors of E are inserted into the positions of F at J, at those positions. Okay, so essentially the same formula from the Shor-Laflamme enumerators, but the difference is we compute the weights of part of the poly operator, and we just leave the other ones alone. Okay, and so this thing can be thought of as a tensor. This is the tensor sum here over the pairs of poly operators, in this case of weight M, and then a similar thing for B. Right, so our goal then is to show that we can manipulate these tensors of enumerators in the same way that we would manipulate the Legos in constructing codes. Okay, so a couple quick properties. If we take the tensor product of two of these, it's just the tensor product of the associated enumerators. And so that is if you take two blocks of codes and you want the enumerators of both of them, well, you just tensor product the associated enumerators to get the enumerator of the block. All right, so the obligatory McWilliams identity is here. And so we never have to construct the B tensor enumerators. We can always recover them from the A tensor enumerators. It has the same form as the McWilliams identity for ordinary quantum enumerators, but now we have this additional transform. This is just a generalization of the Wigner transform. Okay, and therefore, we see that the McWilliams transform and that is really a type of Wigner transform. All right, so the main result is basically summarized as follows, that the trace of the enumerators is the enumerator of the traces. Okay, so over on this side, we have the traced Legos to create a new code here. I want to know what's the enumerator of that new code. Well, I just compute the enumerators of the codes individually, and I trace those things together. Now, I have some tensor products that I've sort of suppressed in the notation here, but that allows us then to build the enumerator for the large codes from the enumerators, which we can construct explicitly for the small Legos that we build it from. So for instance, we've seen the surface code. So here, when we trace them together, each of the enumerators for these small 422 codes are easy to do. And now when I write down the enumerator for, say, this one code, and I trace it into the enumerator for this code, I can compute the enumerator for their trace just by tracing the appropriate enumerators, and just continue that process in rows until I reach the end. And so that's relatively efficient. Okay, it's still going to be exponential in something. In this case, it's exponential in the sort of cut size of the network. But so, for instance, 181 qubit surface code of distance 10, naively, that would be something like 2 to the 80 enumeration of weights of stabilizers. But here it's we can do it quite quickly. I've listed out the first few examples here. So notice the A counting stabilizers and the B counting normalizers are identical as one would expect until degree 10. But notice even more importantly that how many logical operators are there that are non-trivial, just a very, very tiny fraction of all of them, which is indicating the good code property of the surface codes. Rotated surface code, it's exactly the same thing. If you look at the network, it's not, is this really any different than the previous network? And it's hard to actually see any difference. Flipping back a slide, if we just say cut it out of the middle triangle here, even that's the rotated surface code, is just cut out the middle piece here. Otherwise, it's exactly the same computation. So we can get up to distance 16 of this thing without too much difficulty. This would be cryptographic work if we tried to do it naively. This took about 20 minutes on a laptop. It wasn't my laptop. It might have been more than 20 minutes on mine. It's not very good. But this is actually computing these enumerators exactly in closed form over the integers. So there's no approximations. It's just we get the exact answer. All right, so coming to the end here, color code, same sort of thing. We've seen that each of the little Steen codes here, the tiny ones, can be constructed from the more basic Legos, but if we treat it as an atomic Lego itself, here's a tensor network formalism for it, and we can construct, say, the enumerators, exact enumerators for a 91 qubit code here. Very, very straightforward. All right, so coming to an end, a couple of open questions. Obviously the topics for the day is, how do we make quantum LDPC codes really work for us? And so the question that I have is then, well, can I find a simple Lego construction for these things? Because if I can, then there's a good chance I can write down their enumerators explicitly and get exact distances, and in fact, a lot of the additional properties from those. All right, because we extend these instructions to analyze fault-tolerant circuits. The answer to this is yes. Stay tuned. I was hoping to have an answer today, but maybe a little bit later this week. And then finally, can we use tensor enumerators to predict how to build good codes from Legos? So in other words, can I machine learn or AI learn how to build codes? Well, what I need to know is how does their enumerators behave when I grow them and then shrink them through tracing? Okay, and now that we have some method for actually doing that in an efficient way, it seems a very tractable problem. Don't know the answer to that one yet. All right, great. Thank you very much, and happy to take questions.
Okay, are there questions?
Can you do anything with dynamical codes with this?
Floquet codes. Okay, that should have been one of my open questions. I talked with the guys at University of Maryland a lot about this, and the answer is I don't know. All right, so we thought we had some ideas, didn't quite pan out. We thought we had some new ideas. Maybe they will pan out. It's still a work in progress.
Okay, maybe one more question.
So in one of the earlier talks today, we learned about how the ZX calculus could, help us sort of change from one type of code to another. Mm-hmm. Is something like that possible here, or?
Maybe. I don't think there's any easy answer to that. So there is certainly a similarity between what's going on in the ZX calculus and what's going on here, because they're both based on tracing together networks, at least at a fundamental level. But the objects here, it was just a graphical language. It wasn't anything specific. So we're in the ZX calculus. One of the spiders represents something very specific. And so if you write down a different spider, you get something else. Here, I just wrote down blobs to represent a code. Right, and so in many ways, you can change from one code to the other, but you don't see it in the figure, right? So it's exactly the same network, exactly the same structure. And so, so we've sort of kept it at a structural level. And so, I don't think there's any real answer that I can give.
Okay, in the interest of time, let's maybe take all other questions offline. Let's thank Brad again for the nice talk.